Hello, this is Good Nedgiri.
This is Ryan Parsons.
And this is Connor Goff on our presentation of 3D printed exoskeletons in stroke rehabilitation.
A stroke which damages or destroys pathways in the brain.
In the United States, roughly 7.8 million adults have experienced a stroke. Of these 7.8 million, roughly 35 to 40% experience long-term mobility and movement issues. We are particularly focused on the stroke belt in the southeast United States, where stroke rates are higher due to lifestyle, diet, and most importantly, limited healthcare access. Many people in this region are also on fixed income or have lower income, which means they can't afford expensive rehab care or long recovery sessions. And that is where solutions like ours come into play. They are needed since they are lower cost and more accessible, especially for people in these areas.
For the solution brief, we use low-cost EEGs and affordable 3D printed materials to create accessible exoskeletons. EEGs map brain signals that are not reaching the right muscles. 3D printed exoskeletons assist movement and support rehabilitation. Current devices cost tens of thousands of dollars and are not accessible for low-income areas. Lower-cost EEGs are in development, but exoskeleton cost is the biggest concern. Exoskeletons must be personalized to each user and their remaining limb movement, and users must be fitted so the device works for their specific needs.
For our main visual, we are showing an infographic that represents our solution, a low-cost EEG controlled 3D printed exoskeleton for stroke rehabilitation. This device uses a simple EEG headset to read brain signals. Those signals are processed in a real time and translated into movements of exoskeleton, specifically finger flexion and grip motion. The visual highlights how our brain signals are captured, how they activate the device, and how that leads to recovery of our hand mobility. On the right, we also have included a small performance chart. It typically shows how improvement is seen in the stroke survival using EEG control exoskeleton. Like the finger flexion is increased, grip strength improves, and the task completion time decreases. These improvements supports the idea that brain machine rehabilitation can help stroke patient regain movement more effectively and at a lower task. Another thing is like existing technologies. Our solution builds on several existing technology that already exist in today's life. Like we use low cost EEG headset like OpenBCI or Muse. We rely on brain machine interference or BMI signal processing pipelines. For physical structure, we use open source 3D printed exoskeleton design. Also, we use microcontrollers like ESP32 for onboarding processing. And some of the design shortcomings are, even though the designing promising, there are several important limitations like cost and access, fit and comfort, EEG noise, which is it affects by the movement or the electrical interference, and the safety concern, regulator holders, and there there is user learning curve too. And finally, the durability and power. Overall, our concept is promising and affordable rehabilitation, but these challenges highlights area where future development is required.
Our grand challenge for this project was reverse engineering the brain. At a basic level, a stroke is when blood flow to the brain is cut off for a short period of time, and this leads to long-term nerve damage. In order to improve life after someone has a stroke and recover from the nerve damage, our exoskeleton uses EEGs to help regain their movement and functionality. Through studying the brain and better understanding its inner workings, our exoskeleton can better interpret these brainwaves. By improving our understanding of the brain, our exoskeleton can help improve even more people's lives. If we were to continue moving forward with this project, some of our next steps would be to seek funding for our project and gain intellectual property protection rights through patents and grants. We would also have to look for clinical and research partnerships with rehabilitation centers so that way we could support our trials and gather users. We would also have to conduct early stage testing with lab simulations and small pilot trials. We would also have to get approved by the IRB and FDA for trials and human use.